You can put your slide up, Ebrahim.
Okay.
Morning, everyone. Welcome to the second day of the Data Science and Industry workshop. I'd like to welcome all of you and hope that today is as interesting as I think yesterday was. Our speakers today are both academics at the University of Johannesburg. We have Professor Ebrahim Momoniat and Dr. Vivien Visaya, who are both in the Department of Mathematics and Applied Mathematics. And they are going to be discussing modeling traffic flow through data science. So welcome both of you, and thank you very much for your time today.
Thank you, Sharice. Good morning, everyone. So I'm Ebrahim Momoniat. I'll be going first. After my presentation, Dr. Visaya will carry on afterwards. And yeah, we'll see how it goes. We will have breaks today, probably breaks of about 10 minutes or so, just so that you can have a comfort break or grab a cup of coffee or do whatever it is you need to do. Before I get to my talk, I actually wanted to show this video. It's something Elon Musk did, I think earlier this year, and it just explains why autonomous driving is a hard problem and all the various aspects that need to be taken into account when you're actually trying to do autonomous driving. So I'll just do that. Okay, so that was just a short video that he did, which I thought was an interesting one. So let me just put up my talk. I'll put a link to that video in the chat so that if the volume was too soft, you can all play it by yourself. Okay, give me 1 second. There we go. Good. Okay. So I hope you can all see that. If you can't, just let me know. I will. You can just put a message in the chat if something's wrong with the volume or anything like that. So as I said, we will be discussing today modeling traffic flow through data science. It's myself and Vivien, and right. So The program for the workshop was set up in a particular way so that you can get the most out of it. Yesterday we had SAS speaking, giving us an introduction to data science and how SAS is used in data science. It was a very general talk, and what was nice is they spoke about all the little things that you may not be aware of. Today, Dr. Visaya and I will be expanding on some of the ideas that they spoke about, but more of the big issues like missing data, Q-learning, and using Azure will be discussed later in the week. So you'll see you actually building toward being able to do a big data science problem, or solve a big data science problem by attending these lectures. After Dr. Visaya has spoken, I'm going to carry on speaking to then finish off the session. I will be working with a real example, looking at data, looking what can go wrong with data, looking at all the things you shouldn't do, right? Anyone who I've taught will tell you I always do the wrong thing first, then I do the right thing, so that you can have a feel for how doing the wrong thing can actually look right. And that's the problem with data science, is that when you're cleaning your data, the thing that seems the most logical may actually not be. You may actually have to spend a few more minutes thinking about what you're doing. Yeah. Right. These are references that my part of the talk comes from. All the references that we've used today, we will put in the chat. Anthony will probably email them to you as well. So we've downloaded the PDFs of the articles for you, so that if you do want to get into this area or learn a bit more, you're welcome to do that. And if you think you want to do a postgraduate in something like this, you can just contact Dr. Visaya or myself. Dr. Visaya's other title is Head of Applied Maths, so she's probably the better person to contact. Right. So when it comes to modeling traffic, those of you who drive in traffic, and all of us have experienced traffic in one form or another, there's two ways of looking at it, right? There's the deterministic way, and deterministic means you know exactly what's going to happen when. So time is not stochastic anymore. Time is actually a fixed unit of the process. And deterministic models are not very good they're easy to derive, but they're not very good for the traffic flow problem, for the simple reason that traffic flow tends not to be deterministic. These models are further divided up into the macroscopic and the microscopic. Macroscopic, big picture, you can think about. So this is where you're looking at the relationships between traffic flow characteristics like density, flow, mean speed, traffic stream, etc. Big picture was ideal, I don't know, probably in the early 1900s or so, simply because there weren't as many cars on the road. What's been happening lately is that the interest has shifted to look at microscopic methods. So if you look at it, what are macroscopic models, right? So these are the continuum approaches. So those of you who've done any sort of fluid dynamics, mechanics, you'll know that. Cellular automata. Cellular automata is essentially modeling at its lowest form. I've got a picture of a cellular automata on the next slide, I think. And then kinetic theory of gases. What's interesting about the kinetic theory of gases, this is where you model the cars as if they're gas particles, and they not really bump into each other, but they get close to each other. And when they get close to each other, the other vehicle responds. So if you think of driving on a motorway or driving highway anywhere, if a car is speeding behind you and they catch up to you, one of two things will happen. You'll either slow down because you like road rage. You'll speed up so that you can get ahead of the car, or you'll move, you'll change lanes, right? And that's how gases behave, right? They do those three things. There's either a transfer of energy, if you like, which is a collision. Then there's the particles that move out of the way. or the energy is then transferred in a perfect collision. So that's where Newton's laws of collision becomes important. The biggest issue for us today is congestion on our roads. Whether you're living in a rural area, a suburb, motorway, congestion is a big problem, right? So the motivation for looking at this congestion, as I've said, and congestion is usually because demand is exceeding supply. What that means is the more we can afford cars, the more cars there will be on the road. When it comes to vehicles, there's a perverse logic in terms of what is good for the environment versus us as people, what we'll do. You find there's a lot of psychological research that's been done to show that for many of us, I include myself in this, your vehicle becomes your own personal space. And in that personal space, you have power, you can do things. When someone invades your personal space, well, then things on the road get very exciting. Right. Also, the roads that we use were built in 1940s, 1920s, and they're still being used today. And the video from Elon Musk actually showed that those are the roads that autonomous vehicles have to use. The one thing he missed out on is potholes, right? Potholes in South Africa are very, very dangerous because if you go over a pothole very fast, you're not likely to make it out of there unscathed, right? So those kind of road conditions become important issues to look at, especially if you want to have autonomous vehicles, because these days when you drive close to a pothole, someone normally just swerves out of the way into you, and that's how accidents happen. So if you're away on the road and you're driving defensively, you can actually avoid a lot of the issues around potholes. Right, if you look this picture at the bottom right, you'll see this, it says there Rule 30. Rule 30 is a rule, is an automaton. I haven't put them all the rules in, but essentially what automatons are is the way you build up a solution based on rules, right? So if you start with all white blocks, they move to the next one. If you start off with blocks that look like that, they go to the next one and the next one. So it's a very visual thing. If you look at this picture, this is a black and white, purposefully black and white grainy picture of a suburb with roads. And if you look carefully, when you zoom in, you'll actually see that the vehicles look like cellular automata. They look like automatons on the road. So if you want to use something like cellular automata, what you need to be aware of is what rule of cellular automata is ideal for traffic. That sounds easy. It's not, because as I speak through the different issues around the road networks, etc., you'll see the problem becomes more and more complicated as you go along. The other issue that compounds things is the fact that you now have adaptive cruise control in cars, right? If you've got an older car, cruise control, you just set the speed you want the car to drive at. So it could be 100 kilometers per hour, and you fix that speed, and that's it. The car stays at 100. Sometimes there are sensors in the car that will either slow down or speed up if it senses that a car is close by. But you as the driver at no point take your hands off the steering, right? So that's not fully autonomous. That's adaptive cruise control. What's interesting about adaptive cruise control is that it creates these wave motions in traffic. So if everyone is using adaptive cruise control, the traffic actually becomes chaotic, because it becomes like ping pong balls bouncing into each other, because the car in front responds or slows down, your car slows down, the car behind you slows down, but then the car in front starts speeding up while the cars at the back are all slowing down. So you can imagine these ping pong balls or strings with balls on just moving up and down. Right? Now, a string of vehicles is stable if the spacing error or the deviation is does not amplify upstream. So this is the chaos I was talking about. right? And this is something you need to be careful of. And this can also happen if you have different sized vehicles. So on our roads, we have taxis, we have trucks. These days, a lot of ambulances, and the big trucks in particular cause a lot of problems on our roads. And it's not problems with the trucks themselves, but it's how we as drivers respond to the trucks, right? Either the truck is going too slow and you want to overtake, and by overtaking, you're going to drive into another lane and you're actually going to end up killing yourself and your passengers, or um, you you're stuck behind the truck on a load where you on a road, sorry, where you can't overtake, and that causes psychological frustration, which means that the first chance you get, you're more likely to make a mistake. So all those things come into play when new roads are designed, and trucks have specific times where they can be on the road within a city. So that's also important. There's this thing called headway, and constant time headway is a safety factor policy to ensure that vehicles don't bump into each other. And I'll show you what that looks like. Yeah. So if you look at this picture over here, what you see is three lanes, lane 1, 2, and 3. You can see vehicles are merging from the left if you're traveling from left to right. So that's an on-ramp. If there's a lot of cars, so when we have lots of traffic or a traffic jam, so if you're thinking of Pretoria, for example, there's a few of these on-ramps that always cause problems. These cars joining have to slow down. You hope they don't have to stop completely, but the minute they stop completely is when you have a backup of traffic. So when you look at the design of roads into the future, you want to avoid this happening. So if you notice on the roads now, this entry lane is a lot longer. If the traffic is joining congested traffic, right, what you find is the congestion builds across all three lanes. Now, if you've driven past the golf course on the M1, right, near Houghton, the Houghton exit, just after the Houghton exit, there's a Houghton entrance, an on-ramp onto the motorway. That's where this happens, because everyone who's joining that lane wants to move across into that lane, especially early morning, because they don't want to get stuck in the traffic that's going to Sandton, right? Because these two lanes, lane 2 and 3, are used by cars going to Sandton to get off the motorway. This situation here, I've seen a lot on the concrete highways, so the national roads, where the roads are just busy and all three lanes are busy. You don't have this free-flowing first lane where these cars go into lanes 2 and 3 because they want to get off at Sandton, and all the cars in the right-hand lane are going to Pretoria, right? So that you're more likely to see all three lanes congested on the national roads. So those are the concrete roads. So it's the N1, N3. There's no even numbers. So yeah, right. And this is the M2. Sometimes has this as well. That's the road to the airport. And then the M1, M1 North, M1 South. Okay? So if you treat traffic flow as a large collection of vehicles, right, instead of a continuum, what happens is you have to then look at each vehicle and how each vehicle is behaving, and you then get an aggregate response. So that's essentially just taking the mean. So what happens is, and this is a mathematical thing that you have to do so that you actually can prove things like convergence, etc. You actually assume that there's a countably infinite collection of homogeneous interconnected dynamical systems. And each car, essentially, you assume is its own dynamical system. You build up the dynamics of each car, and then you add in the other cars, and you run your system to see what's happening, right? So when you model, there's three possible parameters. And surprisingly, there's only three, given how complicated this motion is. There's the number of vehicles in a section, there's the following distance, and the speed. And just using these three things, you can actually model very complex traffic flows. So those of you who are thinking of getting into the autonomous vehicle industry, right? Literally, these are the three things you have to worry about. All the other things that Elon Musk referred to, that comes after, because that has to do with the visualization aspect of autonomous driving. We're looking more at the way cars interact with each other, right? The visualization aspect is the one that he was speaking about, where you have to worry about shadows, you have to worry about potholes, you have to worry about whether or not you can, even if the speed limit on a road, say, is 100 kilometers per hour, is it actually safe for you to go at 100 kilometers per hour because of the road conditions? Those of you who drive a lot in Johannesburg, you'll know when it rains, there's certain parts of our roads that get flooded, for example, right? So an autonomous car would have to take all that into account and probably remap routes to get around those kind of things, just to keep you safe, right? This point here, so driving behavior in an uncongested regime is different from congested. I'm guilty of this. When there's no cars in front of you, 120 is not a rule, it's more like a guideline. But when you're driving at that speed and you start running into a traffic jam, you end up having problems because you then have to slow down faster than everyone else. So Tato's made, yeah, that's correct. You'll see our roads have remained the same for decades, yeah, in the chat, and that's correct. That's why South Africa is trying to do an expanded civil works and public works project, but COVID kind of damaged a lot of that. The psychology, this I spoke about earlier, the psychology of drivers, and the psychology is also a two-way street, right? If you are someone who's a scared driver, so you're scared you're going to die every time you get into a car, you're actually not a careful driver. You're actually more likely to make a mistake being extra careful. I've been lucky or unlucky, depending on your point of view. I've driven in the US. The unwritten rule in the US is you drive as fast as the car in front of you, right? Which generally means you exceed the speed limit, but there's less accidents because everyone tends to keep the same distance between each other because of that. The minute cars start slowing down, everybody slows down because they're just following the car in front. So you can get this weird oscillating behavior in the traffic, but the number of accidents are reduced significantly, or the speed, accidents caused by speed are reduced. So if you think of the Autobahn in Germany, same philosophy. There's no speed limit, but what tends to happen is everyone tends to drive as fast as the fastest car in their vicinity or in their part of the motorway. And that's generally based on your eyes or your perception. So if you can see 2 or 3 cars ahead, you tend to try and push so that the 2 cars in front of you are going as fast as that car. That obviously leads to a lot of road rage, which is why autonomous vehicles are becoming more and more important. Point number 3 over here, the product of the distance and the number of vehicles, when you sum across all possible cases and classes of vehicles, should be smaller than the length of the section. So what does that mean? It essentially means that if the length you're going to divide your highway up is, say, 1 kilometer, right? The number of vehicles that are in that length of road mustn't fill the road, because if the road is full, it essentially means the traffic's at a standstill. So then you don't have flowing traffic anymore. You just have zero traffic motion because everyone is stuck, right? So some mathematics, I'm not going to do too much mathematics because I'm not going to assume everyone here is good at ODEs or PDEs. But if you take the 3 things that I spoke about earlier, and the 3 things were, so it's the following distance, that then becomes the rate of change with respect to time. So that dot is just a derivative of that, and the speed. You can say that the change in speed or the acceleration is a function of the speed, the following distance, and the change in following distance. So when we write out general models like this, any data science problem starts off like this, right? Where you have to ask yourself, what are the variables that are going to impact on what it is I'm looking at? sometimes you need more, sometimes you need less, sometimes you have more or have less information than what you need. This just depends on the context of a problem. This quantity here, for example, you can calculate from that one and that one, right? So if you know capital N, the number of vehicles, you know the following distance, and you know the speed, if you follow a particular vehicle, you can usually calculate that one. So with models like these, you may not necessarily have all the information, but you can calculate missing information from information you do have. So that's not really a big issue here. The important assumption you have to make sometimes when it comes to modeling is that vehicle behavior is stable, right? And that's the example I spoke to you about the ping pong balls, and you getting chaotic behavior coming up, especially if you're going to use kinetic gas theory. The reason you assume your string is stable is so that you know you can use a computer, or you can use basic numerical analysis to solve this. Dr. Visaya will show you, I think there's 2 cases she has where things are chaotic. What do you do? How do you handle that from a computational perspective? So she'll discuss that with you, right? So this is exactly the same as the previous formula, except the bars mean it's an average or an aggregated quantities, which means for each car I, you have an equation like this. Generally, you either have to sum them, or you have capital N equations if there's N cars, and these quantities are related to each other, especially the following distance and the change in the following distance, right? And this is also something important. The difference between the aggregate speed, so the average speed in one section and in the section afterwards. So say you've got 200-kilometer sections. You assume the traffic may slow down in the downstream section because there may be more cars there. It may speed up if there's less cars in the next section, or it may stay the same if everyone's moving then at a constant velocity, right? So those are the 3 stable cases that you have, right? But if those are the 3 stable cases, it basically means contribution from relative speed is 0. So what does that mean? Now, when you model things that are moving, you have, okay, I'm going to say 2 options, but these days there's probably more. In the one case, you can be an observer that is moving at a fixed speed along the highway or the road, and everyone else is moving relative to you. So what that means is if you're an observer on a moving car, say traveling at 60 kilometers per hour, anyone traveling at less than 60, it'll look like they're going backwards. Anyone traveling at more than 60, it's going to look like they're going forward, they're going ahead of you. Right? That's the one way of modeling. You model that way. If you ever see in the papers, they speak about Eulerian or Lagrangian, right? So that's Lagrangian because then you're part of the system, right? With Euler, it's a lot easier. You are an observer that is completely outside of the system, and you can observe the system. I'm going to show you later, there is a law in thermodynamics which says the minute you observe something, you change it, right? And if you think of your own experience, if you see those lines across the road that are counting vehicles, you slow down, which means that the instrument that's there to measure things like speed, number of vehicles, etc., is actually causing a change in the way drivers use the road. So that's something that if you do get into this, you have to worry about, because you want to have a system of measuring that doesn't interfere in the traffic, right? And of course, with IoT or the Internet of Things, that's become a lot easier to do. Oops. Right. So I spoke to you earlier about roads joining and changes being made where this part that joins is longer. Right. So here you see vehicles joining from the left. By having a longer stretch of road for vehicles to join, you actually don't create that ping pong oscillation in the traffic. What actually happens is that these cars that are joining the highway actually find it easier to join the highway. Same thing here with this picture here. This would be a typical picture where there may be 2 or 3 lanes there. two things have to happen here. These cars all have to become one lane. This one lane then has to join this 3 or 4 lane highway. Right? The average speed here is probably half the average speed here. Right? So there it might be 60 or 75 kilometers per hour. Here it's probably 100 to 120 kilometers per hour. To accommodate that distance or that joining distance over there, to make sure that these cars in that distance can actually reach the average speed there, which is probably 100 kilometers per hour. You have to make that longer. Right? When do accidents occur? Accidents occur if a driver that's here suddenly panics and either stops or slows down so much that the cars behind are caught unexpected. Because then a car behind either tries to join that lane to avoid bumping into this car, but then bumps into a car there, or this car actually bumps into that car because they assume everyone in this part of the road is accelerating to join the highway, and they don't pay attention to what's actually happening. So they actually miss, your eye will actually miss the fact that this car stopped. So when I speak about the eye, I'm generally speaking about perception. So it is the perception of the individual about what's happening in the traffic. Right. Of course, being an applied mathematician, I like having formulae. So essentially, this is the formula that relates how the change in the number of cars in one section is a function of the changes in the number of cars plus the average of the number of cars. And that kind of does make sense. And this is a continuity condition, so that if you divide your road into 1 kilometer stretches, where one section joins another section, all the cars that are on that boundary cross over into the next section, which basically means that your entrances and exits of the highway are midway. The best strategy is to not have them at the boundary of a section, but preferably midway, so that you can then count how many vehicles have left the highway. And that's what that does. That's what that picks up. Okay. So that's the main line flow. That's the one we're trying to get. It's V, and then it depends on this L. And if we just go there, it's on the check. So that's the distance, right? And then the average following distance. So all of this makes sense. So if you put all of this together, you end up with a system of equations that looks like this, right? You have an equation for each vehicle, basically. So 10 vehicles, essentially 40 equations, right? 100 vehicles, 400 equations. So this problem, you can see, blows up very, very quickly. However, because computers have become very powerful, yesterday you've heard about GPUs, how GPUs are used, you can actually do this now. The other thing that helps is that most vehicles have got vehicle tracking software in them. And if you contact Tracker or any one of the tracking companies, and you ask them for not specifics, they won't give you specifics because of POPI, but you ask them for essentially data for a particular stretch of road where the data includes speed of the vehicle, etc. They can generally give that to you, but by anonymizing the data. Those of you who have Discovery insurance, you know that Discovery charges you more if your rate of change of velocity, so your acceleration, is very jumpy, right? Because that means you're almost like an impatient driver. You're not a safe driver. They also monitor the distance between vehicles. So are you one of those drivers who speed up and then almost hit the brakes when you come to a vehicle that's in front of you? And then there's a third one. I think it's looking at traffic behind you, right? So you don't just stop the car and then a car bumps into you, right? So there's about 3 or 4 cases that they monitor continuously to make sure that no accident happens. Okay, right? So that I've spoken about. Okay, so these 2 pictures. This is the US. That's China, right? If you read a few years ago, or in fact, no, not 2019, so 2020, 2021 are COVID years. Before that, China had the world's biggest traffic jam, where literally every single car just stopped on the highway. people were bathing alongside the highway, they were cooking, mini restaurants opened, because it took them a week or so to clear up the traffic jam. So we more aware of what's happening in China because of COVID and how COVID spread there. But generally, when they have the Chinese New Year holiday, that's when this happens. It's where everyone decides to drive to rural areas, etc., to go home. And yeah, so they have really bad traffic jams. If you look at this traffic jam here, even though it looks like there's a lot of cars, this traffic actually moves. Right? It may move very slowly, but it moves, right? When you compare to this, where everything was at a complete standstill, versus this, where the roads are full, but it's actually moving. And this is because of the various rules of the road that have been introduced. Like I said, in general, you travel as fast as the car in front of you. You don't put unnecessary barriers in front of drivers to make driving difficult. You actually make driving easier. Right? Now, the one thing to note is that when the following distance is small, it's hypothesized that drivers will then tend to keep a safe following distance. And so essentially, when cars are closer together, the assumption is that people are better drivers or safer drivers. That may or may not be true depending on which road you're looking at or where the people are coming from, and also the condition of the road. So if the condition of the road is very poor, sometimes it's not easy for everyone to slow down like this. If the road is uncongested, drivers tend to maintain a safe following distance that varies with the speed. Right? So so when people are going fast, ideally, that's what you want to have happen. Accidents happen when this is not the case. Right? And then we introduce this constant. So essentially, there's a switching that happens. So number of vehicles in one section is greater than that quantity. Remember the multiplication. Then vehicles try to maintain a constant following distance. Otherwise, the vehicles are trying to create a distance that is a function of their speed. So that's the one I spoke about in the US, where everyone drives as fast as everyone else. Right? For the purpose of simplicity, we'll assume that vehicles follow a constant time gap in this regime. So that's the regime where everyone is trying to follow each other at the same safe following distance. Also, if following distance are reasonably large, vehicles are assumed to maintain a free speed. So that you can think of very early in the morning before peak time traffic, or after peak time traffic. That generally happens. And then you add in these three constraints, right? So those of you who've done optimization, these are constraints that you add in, and your full set of equations then look like this, right? That looks like a complete mess if you want to solve that, but it actually isn't. Most of this comes from information that you have already. And those of you who read the journal articles that I'll put on for you, you'll actually see it's all in the articles. So while Dr. Visaya is speaking, I'll actually put the journal articles up for you, right? And you'll actually see where the system of equations is solved. Now, when I say solved in the case of a data science problem, it's not like saying x plus 2 equals 2, so x equals to 0. Right? This is a simulation. So what will change with this at each point in the simulation is your initial condition. It affects the outcome. Right? So if initially you have only 10 or 20 cars in a stretch of highway that can accommodate 200 cars, what your simulation may show you is that when there's less vehicles, less traffic, vehicles drive a lot better. Right? When there's more cars, more traffic, then there's more of the stop-start driving that happens. So all of that will come from this model. Okay? Now, if you split your model up into the speed that a vehicle would drive and the number of vehicles and over time, right? You see that when you just plot the raw data, so the blue is just the raw data, and I'm going to show you that raw data after Dr. Visaya has spoken. And we're also going to give you the Excel spreadsheets so that you can also try this. Right? You can play around with this. when you model speed, so everyone's 60 miles per hour, so that's close to it's almost 100 kilometers per hour. Then there's this massive slowdown. And if I were to ask you, why is there a massive slowdown, right? If you look here, there's a spike in the number of cars, right? When does that happen, right? So if you think about when is there a spike in the number of cars over a half an hour, no, let's say over a 2-hour period, 1.5 hour period. Well, that's peak time, right? So if you have traffic that's normally just going along and suddenly the traffic slows down, you know there's either been a major accident or there's peak time. Then it carries on. So the blue's the data. That's a fitting that we've done. Like I said, I'm going to give you a nice two laboratory exercises you can do on your computer in Python, and you'll be able to actually do something like this. And then that's the number of vehicles. Now this is so rather than measuring distance here, they've just measured traffic after every minute. Years after every 5 minutes, you can see that there are less points, but your model still captures quite a few things. Your model has a spike there, and if you look at this one, there's no spike, right? These spikes would tend to happen because the number of data points are not sufficient for resolution, right? So the resolution is how good the quality is of your curve, right? So if you have fewer points there, this tends to be what your data science algorithms will do, right? And there's the spike. You can see the spike more in 5, because we're now using a 5-minute gap. On the one side, you'll see a lot of vehicles. On the other side of the motorway, vehicles decrease, right? So generally, if you think of driving from Johannesburg to Pretoria, there's a lot of congestion going to Pretoria in the mornings, a lot of congestion coming from Pretoria in the afternoons. That's essentially what that's picking up. If you look at it in 10 minutes, 10 minutes gap starts smoothing out the data, but not the curve, because now that becomes more pronounced, right? If you look at number of vehicles now, this also, all these curves here now become more spread out because of the number of data points that are available. And then obviously 15 minutes is the last one. So you see, you can actually zoom in on each one of these sections here. So you can see the model, when it comes to looking at the number of vehicles, give you something that's periodic, right? So this is the wave I was talking about. It's almost like it moves through in what's called packets. Those of you who are interested in quantum computing, quantum mechanics, those are the quanta of the waves that are moving through the system like that. Okay, of course, here that peak is much higher than it's been previously. But also, if you look at the bottom here, you'll see what's creeping into the problem is all these funny, almost singular behavior. As someone who does mathematical modeling, when you see things like this happen, you need to ask yourself, is this a function of the actual traffic? Is this a function of the data modeling the traffic? Or is this just an error, right? Because where you have singularity, it generally means one car is on top of the other, right? That's essentially what that means. But you'd have to look at accident reports, etc., to see if there was actually an accident. Right? But generally, that type of thing, you'll have to look into in a lot more detail. Yesterday at the talk, they mentioned the insights you can get from data if you look at your data using a different lens. So if you look at maybe only this part of the data, there might actually be something happening here, a merger of lanes, for example. So 3 lanes going to 2 lanes. So this is actually a real phenomenon. That's a real change of behavior, right? But if that's not the case, you then have to redo your numerics or your computation with a different algorithm, right? Macroscopic models, just briefly, philosophy is different here because now we're looking at a collection of vehicles. And you can see from this this picture here where you're looking at the number of vehicles. Looking at a collection of vehicles may not be a bad thing, because you can see how this group moves there, right? As time evolves, you can see that you have these packets of vehicles essentially moving through the system. So that may not be a bad assumption to make. Fundamental diagrams, you'll see the title of the papers that I'm going to give you have this fundamental diagrams in. What's key is vehicles per hour, so the speed kilometers per hour, and the traffic density, which is vehicles per kilometer. In terms of macroscopic models, we actually have very good models, right? And this picture here is just to show you, this is fairly intrusive interference in the traffic, because the minute you see these cops sitting under a tree, everyone hits the brakes and slows down, right? And that's generally also where a lot of accidents happen. Here is more silent monitoring of traffic. This case you have when they put speed traps at fixed places. What happens here psychologically is the minute people who use that road often know where the speed traps are, those are the people who slow down. The vehicles around those people either slow down or overtake to speed up. That is where lots of visitors to an area, for example, might get traffic fines, right? And trust me, the cops know this because the road's been modeled, so they know exactly where to put these things so that they can optimize their return on investment of this camera, right? The data will have density and velocity data, and this density and velocity data goes into this. The one thing I want you to notice is this model here has got a log, right? You can't take the log of a negative number for obvious reasons, and sometimes when you take logs of decimals, you get negative answers coming up, right? So this model here, even though it's a very popular, you see this name Greenberg in a lot of the literature. This model here has its own inherent problems. Exponentials that I'm sure all of you know, that exponential is basically saying you have exponentials moving through the system, right? You model each one of these as an exponential. So the density of the vehicles in the center is bigger than the density at either side. Okay, that's essentially what that means there. These depend on one parameter, that's density kj, so it's the density in a particular point or a particular length. Vf is the free-flowing speed. So if there was no traffic, how fast would you go? So that you would generally take to be the maximum speed. There's newer models that depend on more than one parameter. This is 2, it depends on V naught and the K. 3-parameter models, you have this lambda coming up. Now you can guess, right? Because of data analysis, more data being available, these things are more popular, right? They are higher parameter models, right? So generally, the one thing that I didn't speak about was that when you model traffic flow, generally we try and do it holistically, right? So when researchers look at this problem, it's trains, planes, and automobiles, right? You probably heard that being said somewhere. What you want to have is in areas where the traffic is very dense, people are using public transport, right? So maybe taking a train to travel over a very longer distance, or using a plane. So traffic from Joburg to Durban tends to become very congested. To minimize the congestion, you either have trains or planes, or you have the situation where everyone is racing to get to their destinations, right? You don't want to be late for a meeting, you don't want to be late for a date, you don't want to be late for a funeral, various things that drive us in our lives, in our daily lives. So you don't want this situation to happen on the roads, where everyone believes they're a Formula One driver, and bad things tend to happen here, right? These models become important because they're used to determine a road's carrying capacity. So earlier on, we spoke about public works projects. And if you look at public works projects, those are driven by these speed density models and what they say. If you look at innovation in this area, so if you someone who thinks innovatively, or you're thinking of how does one form a business in this, if you are able to work with data modeling, etc., in a way that's efficient, effective, you can explain things. You'll find that roadworks, for example, is always looking for consultants who can help with putting these together. So if you're someone who wants to be a consultant in this field, for example, a McKinsey may hire you because they've been hired by City Council of Johannesburg to model traffic on our motorways, right? Do we need more airports? Well, the more airports we build, the more road infrastructure we have to build to be able to take passengers from one place to another, right? Same with trains, same with cars, right? As cars become cheaper, there's more cars on the road. More cars on the road means we have to design better roads. What's happening because of environmental impact assessments, governments try to push people from cars to trains. Companies that advertise, most of them want to get you off a train into your own vehicle, right? So people who sell cars all want you to have your own car. That's just the different drivers in any economy. Planes, well, you all know what's happened with SAA. Traveling by air is tricky because it's costly, but does the cost benefit of taking a plane outweigh that? Because if it does, I think in places like India, there's a lot of subsidization of aeroplanes, so that the tickets are not as expensive and people are encouraged to actually use planes. Okay? So that's my first part. Are there any questions? Now you can put your question in the chat. But while we're waiting for questions, we'll actually have a break from now until I guess 10:05. Vivien, will that be okay?
That's fine.
Yeah, and then you'll start at 10:05. Okay, cool. So we've been going at this for almost an hour. So yeah, we'll have a 15-minute break now, and then we'll take it from there. So if you have questions, please put them in the chat, and then I'll answer them while during the break, okay, or when we get back. Okay, thanks, guys.
Ebrahim, there's a question.
I'll answer it at 5 past when everyone is back, and then we'll carry on.
All right.
Okay, guys, I've got it as 4 minutes past 10. I'm just going to answer a question that was put in the chat. It said, what will be velocity of change in multidisciplinary approach to intelligent built environment systems and dynamic systems thinking for multimodal hybrid transportation models that are multifunctional built, right? So I'm going to answer this question different, I guess, to what you would expect, because I will base it on the talk that was given yesterday, and also some of the technology we see coming to us. So in the first instance, modeling is becoming multimodal. Now, if you look at a discipline like mechanics, for example, so Newton's laws, etc., what you have there is multi-phase flows, or multi-phase modeling, if you like, where you models now are able to take, for example, when water is converting to ice, they're able to model that in between stage where water's just become ice, or if you have ice melting, it's the other way. Now, the reason I'm using that example is because it's the same as multimodal stuff, because that crossing point from water to ice, for example, it's where passengers would move from one mode to another. So modeling has become a lot better. There's been a big improvement in computing and computing facilities. So now if you want to do big traffic flow problems, you can use the CHPC, the Center for High Performance Computing, for example. A different way of looking at this is to say that what happens now in industry is that you have different teams that look at these problems. So the teams are made up of psychologists, philosophers, mathematicians, engineers, computer scientists, etc. And the reason you have multidisciplinary teams looking at these problems is because the role of psychology in how we travel has become more and more important. So irrespective of what conclusions you reach as someone who is modeling traffic, a psychologist needs to look at it and say to you, well, no human being on this planet behaves in this way. So even though you've got this beautiful model, you're missing something, right? So, excuse me, assuming everyone on the road is angels, right? Why do we have accidents then, right? So assuming everyone's going to follow the speed limit, why do we have accidents? Why is speeding such a big problem? So there's a psychology there that needs to be looked at to say that, look, if we want to improve road safety, we want to improve carrying capacity by having multimodal transport systems, how are we actually going to get people to use them, right? A classic example of this is there was a university, I think in the US, that put bicycles on campus so that students could use these bicycles for free to go from one part of the campus to the other. No one used the bicycles, right? They were there, students had asked for it, but no one used it. The maths was perfect in terms of where to put things, etc., but it just wasn't being used. They then brought in a team of psychologists to look at this, and what the psychologists found was where the maths said you should put a station is not somewhere where students would necessarily go past anyway. So what had to happen was all the stations had to be moved so that the maths then is not the perfect solution. It's an approximately good solution. But psychologically, people were more likely then to make use of that new mode of transportation on campus. So vehicles were banned and everyone then started using the bicycles that were there. Same as yesterday, they spoke about the example of a shopping mall, like Woolworths, for example. Woolworths, Pick and Pay, Checkers, anyone, take your pick. The suites are always at a level where young people, students, teenagers or kids, toddlers, etc., can get to them, right? So if you walk through Woolworths, you'll see the bottom where you're queuing to pay. The bottom shelf has always got the nicest suites, right, and the most colorful, because your eye is attracted to color. Kids will grab that and obviously throw in a big performance because mother or father don't want to buy those sweets for them. right? So all of that is psychology with traffic. And in fact, a fuller answer to your question will be, you start off with a team that's responsible for doing the modeling. You make sure that the people on the team have the right skills so that the solution or the answer people come up with is one that makes human sense, right? It's one that human beings will actually make use of. Okay, and data science has actually empowered that because there is just so much data around psychology available. There's data around traffic. There's data around the age distribution of drivers. So as you get older, do you drive differently, right? So all of that is actually available. You have to look for it though. It's not easily available or readily available, but it is there. Okay. Vivien, I think that's it. So I think you can start.
Thank you, Prof. Momoniat. Okay, hi everyone. So the part 2 is more on the dynamical systems of the understanding the models. Okay, I'm sure I've seen some of you, some students, some third year and honor students, so you probably have an idea what the dynamical systems is, but let me just formalize it for those who don't. Okay, so a dynamical systems is just system whose state evolves with time over a state space according to a fixed rule. Okay, so in other words, so there's two ingredients to a dynamical system. So it's a pair, X and F, or Fx. Okay, so X is the state space and F is the rule. Okay, so it acts on each point, small x, in the space X, okay, and goes through this iterates of X to know the evolution of or the behavior of something whose initial condition is X. Okay, so there are two types of dynamical systems depending on T, the time, okay, if it's continuous or discrete. Okay, and Prof. Momoniat in his talk already discussed what these are. Okay, but just to give you the term, okay, if you use a continuous time system, the dynamical system is called a flow. Okay, and you've encountered this. Okay, these are sets of differential equations. If your time is a discrete time system, if t is a discrete, okay, meaning from could be negative number, negative n to plus n large, okay, then your dynamical system is called a map. Okay, and it's a set of difference equations. Okay, so either it's a discrete time system, which is a map, okay, which you've encountered probably numerical analysis when you want to discretize. Okay, so for Euler or RK, yeah, so that's discretizing your system. And then for continuous flows, these are differential equations which you've encountered in either second year or honors differential equation. Okay, all right, so what are examples of dynamical systems and some textbook examples that you've encountered? Definitely population dynamics or the pendulum, right? So if you were asked to derive an equation of motion of those systems, then you've encountered dynamical systems. You just don't know, perhaps, or it's just a term that wasn't all dynamical systems. Okay, right. So I'll just present just two popular fields in dynamical systems, which I'll use later on when I connect to data science. Okay, first is chaos theory. Okay, so this is one very popular example when one wants to discuss chaos theory. Okay, the Lorentz system of differential equations. Okay, so for these parameters, you actually get an attractor. For beta close to 8/3, you always get something like this, which is called sometimes a butterfly. Okay? And any chaotic dynamical system always has sensitive dependence on initial conditions. So there are three ingredients for a system to be chaotic, but one that usually is popular is sensitive dependence. It means that any small difference in the initial condition, okay, will produce large difference in the long-term behavior. Okay, and this is what you call a butterfly effect. So if, for instance, here, if you look at my cursor, right, if I want to follow this trajectory, okay, of this initial condition, okay, by taking something close to it, even, no matter how small, okay, it could be that for the first iterates, it could follow this trajectory, but at some point it will have a large difference. Okay, so that's sensitive dependence on initial condition. Okay. Okay, the other one is fractal geometry or on fractals. Okay, so this is again an example of a popular field of dynamical systems. So this is what do you call this? A Mandelbrot set. Okay, so it just collects all of those complex numbers that satisfy this rule. Okay, so if you collect all of those complex numbers such that it does not, such that it converges, okay, then it's part converges using this sequence, okay, or this rule, then it's part of the Mandelbrot set. Okay, so this is quite popular. So Mandelbrot set, Julia set, where you look at the collection of points in the complex plane. Okay, right. So regarding data science, this is something new. I haven't really um, gone over it in detail, but fractal neural network, okay, is also one field that's emerging due to the topical issue of machine learning and data science. Okay, so if you're interested, this is quite a good read. Right. All right. So another interesting thing now with dynamical systems is that you can always apply it to any problem. Okay. So since we're in traffic flow, okay, I'll present to you one model. Okay, but I won't go through lots of calculations or simulations because Prof. Momoniat already discussed one model where he did some simulation. Okay, so if you're familiar with, recently with the COVID, what we're experiencing COVID, there's lots of models, okay, on COVID, okay, COVID-19, and these are usually this model SEIR, okay, this epidemiology model is usually used in COVID models. Okay, so once you understand that, then if you want to apply it in other scenarios, okay, it could be in crime dynamics, it could be here in traffic or in obesity. Okay, if you understand an SEIR model, an epidemiology model, then you're applying it in a different application or field, okay, will be easy as well. Okay, so this one is an analogy of SEIR model. It's called an Fsbd model. Okay, it's used in traffic flow. Okay, what are the descriptions? F here are the free vehicles, the same as the susceptible population when you think when you think SEIR model. Okay, so I'm sure this SEIR model have been discussed in your dynamical systems or differential equations courses. Okay, S is slow vehicles, B is for blocked vehicles, and D is for discharge vehicles. Okay, so when you create a model, particularly for SEIR, you talk about compartments. Okay, let me see. Sorry, let me just move this. Okay, so this is just the definition of those 4 compartments. Free vehicles are those that are not yet blocked or slowed. Okay, slowed vehicles, those in the slow compartment are those who have been blocked. Okay, blocked vehicles, okay, are in the compartment, okay, where all vehicles have been blocked by other vehicles, and discharge are those, okay, that have already got blocked by other vehicles and got discharged by some means. Maybe they found another route, okay, and so on. Okay, so if you look at it, if you think of Fsbd, okay, as an SEIR model, okay, then the construction is quite easy. Okay, but before that, we have some analogous parameters. Okay, on the second column, okay, are the description of the parameters in an Fsbd model. But okay, it's also similar to those parameters used, okay, when you discuss an SEIR model. Okay, so the birth rate, the death rate, okay, the transfer rate, okay, and so on. So you have 2, 4, 5. I think this is 8 or 7 parameters. Right. So this one, right? So a death rate, okay, in an SEIR model can also be discussed as a death rate in an Fsbd model. Okay. So these are all parameters that you have to consider when constructing a model. Okay. Right. Okay, so this is the compartments that I've been talking about. Okay, so Fsbd is the same as an SEIR model. Okay, those coming in, going out. So this is like the birth, okay, going inside your population, or death, okay, getting outside of your population. Okay, so all of this agree when you construct a model. Okay, so something that goes out, okay, from one compartment goes in one compartment. And if it goes out, it has a negative sign. And if it goes in, it has a positive sign. Okay, so it's basically one way of model construction with this given compartments. Okay, you can see that everything should agree. Okay, all right. So I won't do this anymore, but I could give the code for later, the MATLAB code for later on. Okay, so this is just relating really, okay, how dynamical systems can be used in constructing a model on traffic flow. Okay. Right. So as Prof. Momoniat discussed a while ago, okay, South Africa really, I mean, you have traffic here, but it's not really anything compared to other countries. I mean, I'm from the Philippines, and the traffic here is really nothing compared to the Philippines or Bangkok or Tokyo. Okay. Yeah, I mean, US is it's also not a lot of traffic, at least where I've been. Okay, so these are the world rankings.
Vivien, are you there? Guys, just think there may have been a power loss or something on Vivien's side. We'll just give a minute or so to get back. Okay, guys, sorry about that. I don't know what happened, but I've just readmitted Dr. Visaya, and so she'll then carry on with her talk.
Hello? Sorry, did I disconnect?
Yeah, it looks like you
Sorry,
just
guys.
disappeared, Vivien. I'm going to make you co-host now, and then you'll be able to carry on.
Yes, I'm sorry. I don't know why this. Yeah, I see that my internet got lost, but now I'm connecting to data. Will you let me know where I stopped?
Yes, you made you co-host now, so you stopped where you had the country list for the worst traffic.
Oh, okay. All right. Thank you. Okay, hopefully I don't get disconnected now. I just yeah, so I don't think it's really the traffic that South Africa has a problem with. It's just really internet connection. Okay. Uh where was that now? Sorry. Okay, so as I was saying, we can complain in South Africa. We may complain about traffic, but really see the if you really see the congestion level, sorry, slideshow, it's not. Mm. Okay, so it's not, I don't know why it's not doing, but anyway, so this is, if you can you see my slide? It's just the top, the ranking of congestion level in. Okay, so the number one is Cairo, and Johannesburg is just number 4, which is in the world's 162. Okay, so if you go to the world ranking, okay, number 1 is Moscow in Russia, and this is where I'm from. Number 4, Manila. Okay, so it's really, I mean, from point A, which is like one, even if it's something 1 kilometer from you, when it's traffic, it takes you like at least 30 minutes. Okay, so we're not really that bad when it comes to congestion or traffic. And if you actually search for some studies on traffic flow regarding cities in South Africa, there's really not a lot, or if none. Okay. All right. So, huh. Okay, great. Thank you. Okay, so now okay, we go to data science and dynamical systems. Okay, so recently there's a lot of data or technological revolution, okay, happening, manifested by the rapid growth of data, okay, that we can gather from complex systems, okay, or the increasing amount of complexity of data being generated. Okay, so because of this, okay, this actually asks or demands new ways to analyze and extract information from data. Okay, and sometimes really it's the underlying math principles that could help us understand this data. Okay, so it's really an interplay of ideas from different areas of math. It could be from numerical analyses, from dynamical systems, and even from what Prof. Momoniat mentioned a while ago, even in psychology. You add some of this that can help you understand a model. Okay, so definitely dynamics plays a big role in many systems. What I'm going to present now is how to use, okay, I know this is a very topical issue, how to use neural nets in the context of dynamical systems. In particular, the next slide will talk about the Lorentz system of DEs. Okay, we simulate uh, trajectories using the Lorentz DEs and demonstrate how neural nets can be trained to characterize dynamical systems. Okay, all right. So neural nets, okay, I'm not an expert on this one, but I can understand how it is if I relate it to dynamical systems. But mathematically, how we understand this is that a neural net is just a differential function that maps one kind of variable. Okay, so it's the input layer to another kind of variable. That's the one in the output layer. So the structure over here, right? So if you've studied neural nets, you know that there's an input layer, an output layer, and also like a hidden layer. Okay, so that hidden layer here actually is, you know, that structure. Okay, it's your model. Okay. You have it's like a regression problem. So given an input, you have a target, which is your output. And this thing over here, the model is the neural network structure. Okay, and the goal here is to find the best parameters that give the best fit between the input and the output. Okay, so in dynamical systems, I can look at this as follows. The input could be my state, x sub t, okay, of the system at time t, and the output is my state, okay, of the system at time t plus delta t. Okay, so if you think of what I mentioned a while ago, okay, if you're talking of maps, okay, if you have an x sub n now, okay, and you have a rule f, okay, to get to the next point, you just apply f to that rule f to your present state x sub n to get the next state x sub n plus 1. Okay, which is your output y. Okay, all right. Okay, so I won't discuss a lot of neural nets, but in general, that's how I see it as a dynamical system. Right. Right. So this is the Lorentz map. So actually, this is 100 trajectories of the Lorentz system. Those three equations that I showed a while ago. So that butterfly. Okay, this is just not one butterfly, but 100 butterflies. Okay, so I have 100 initial condition, and I took the trajectories of those 100 initial conditions. Okay, so what we're doing here is as follows. Okay, what we want is to use this data, okay, of 100 trajectories, okay, to train a neural network. Okay, the training data required for the neural network is constructed, okay, from this simulation of the Lorentz system. Okay. Okay. So this is just a MATLAB computation. I have here my Lorentz system, and then I have 3 layers of in my neural net. Okay. And then let me see. Okay, until here, and then this line over here. I don't know if you can see my cursor. I just generated two trajectories. Okay, so first, this is what I fed. Okay, 1, 2. The second paragraph, I'll just say second, the lines 13 to 20, okay, is my training data. Okay, and then I feed it to the neural net, right? Okay, and then after that one, I constructed again, okay, two, okay, I constructed, what's this, J, yeah, so next is I constructed trajectories, okay, using what the neural net output is, okay, and this is what we get. Okay, I have not this. This is what we get. Sorry. Okay, so what I have is the following. The dashed line is the one that was given by the neural nets. Okay, and the solid line is the one that is the true data. Okay, so I started with 2 initial conditions. Okay, so run it using the neural nets. Okay, and this is this output is because of the training data that I fed to the neural net, the 100 initial points. Okay, that's the dashed line. And the solid line is the one using the ODE 45. Okay, so 2 initial conditions here, okay, where the dashed line is the one that was learned from my training data. Okay, and the solid line is the one that was generated using the usual ODE 45 from MATLAB. Okay, so as you can see here, if we graph the X, the Y, and the Z components, okay, of the dashed and the solid curves, okay, you see the following. Okay, so as in contrast to what Prof. Momoniat showed a while ago in his model. Okay, so here the neural net, actually the output for the neural net, okay, at least for time maybe 0 to 5, okay, very much behaves as the real data, okay, from your simulation using ODE 45. Okay, so there's really not a lot of error, at least from 0 to 5. Okay, so it's quite amazing because it's it's sort of really agree, at least for the first iterates, okay, of your T. Okay, but at some point, because of SDIC, okay, they don't agree already. They don't agree anymore. Okay. Okay. All right. So another model that we are going to discuss here is a type of recurrent neural nets model. Okay, and it's called an Lsdm model, which is Lstm. Okay, so it's a type of recurrent net, meaning it uses the output from the previous step, okay, and use it as an input to the next step. Okay, so if you, this is one example of a node of an RNN. Okay, you have a hidden state, okay, an input, and this activation function uses this input, okay, to give you an output. Okay, and those output is what you use for the next node. Okay, so okay, Lstm.
Your forehead on your phone, really.
Sorry, is there a question, Ebrahim?
No. Sorry, carry on.
Okay, sorry, because I can't see the chat.
I know, Vivien, it's fine. You can carry on.
Okay, sorry. Okay, so for an Lstm, it's the architecture is more complicated, but we can still understand it with the following slides. Okay, so why did I choose Lstm to discuss? It's because I tried to look for some models that relate to data science, and apparently the Lstm has given better prediction or performance than most of the other neural network models. Okay, so I tried to see, okay, why is it good? Okay, and it's because of its long-term memory, something that is addressed, okay, something that's a disadvantage in using recurrent neural nets. Okay. So here it's the same. The node is also recurrent, but it has an internal state. So I can see my there, my cursor. It also has an internal state used as working memory space where information can be stored and retrieved over many time steps. Okay, so it looks like a complicated architecture, but we can talk about it using the 3 gates in an Lstm architecture. Okay, so the difference with this with usual RNN is that it has gates, okay, which is its forget gate, which is like forget gate, input gate, and what's the other gate? There's another gate which I'll discuss in a bit. Okay, so here is the input gate. Okay, so we only highlight this input gate. So the input gate only works with the information from, okay, the current input, okay, and the hidden state. Here, the hidden state is actually your short-term memory. Okay, so there are sort of 2 layers in this input gate. Okay, the first layer is the following. Okay, it uses the short-term memory. Okay, I hope you can see my cursor. Okay, and also the current input. Okay, it uses them and it passes it through a sigmoid function. Okay, a sigmoid function It's just a function that transforms the values, okay, these two values, okay, into either 0 or 1. Okay, so either it keeps an information or not. If it's 0, then it means that it's unimportant information. If it's 1, then it keeps it. Okay, so it's the information from this two inputs. Okay, right. So that's the first layer. Okay, now the second layer is this over here. The input also are these two, okay, the short-term memory and the input x sub t, right? Okay, and it passes those information in an activation function called the in this case, it's the hyperbolic tangent function, okay, to regulate the network. Okay, so whatever the answer here, whatever your output here, okay, in the first, say, layer, okay, is multiplied with your output here in the second layer. Okay, and you have here the output from your input gate. Okay, so that's one way of understanding this LSTM, okay, using this input gate. Okay, the next gate is the forget gate. Okay, so for the forget gate, okay, it again takes these two inputs. Okay, okay, these two inputs are again passed through a sigmoid function, right? So it passes through the sigmoid function. And then whatever your answer here, so this sigmoid function has a different, of course, it acts different as the sigmoid function in the input gate. Okay, so your answer here, okay, when you pass these two inputs in this this function, sigmoid function, okay, is multiplied to this long-term memory, okay, CFT minus 1. Okay, and what you get is this this C of t, okay, which is a forget vector generated, okay, by these two inputs, okay, one from here and the other from that one. Okay, right. Okay, and the last gate would be the output gate. Okay, so it's the same description as a while ago. Okay, so whatever you got here, okay, from the forget gate, okay, and here from your output, from your input gate, it gets multiplied. Okay, and of course, each will go through either the hyperbolic tangent function or the sigmoid function. Okay, right. So that's how the LSTM works. But essentially, essentially it's Lstm is just a node that ultimately with a bunch of parameters, okay, where the parameters are being learned during the training. So it's a usual neural network. Okay? It's just that it's more complicated because it has states inside of each node. Okay, so this is an example. It's quite an easy example that I took from this website. So it's an example of traffic data. Okay, so this is data that's gathered every 5 minutes. So I don't know why it's every 5 minutes. There could be a reason why it's every 5 minutes. Even in Prof. Momoniat's discussion, he also had like data taken every 5 minutes. Okay, so we run this in Python. Okay, we run this in Python and use the LSTM imported from Keras. Okay, so that's the code which I can also give you later on, and you can play with it. Okay, and this is the result. Okay, so the true data. Okay, well, in the data that was in that website, you're given a trained data and the test data. Okay, so the true data is in blue, and the LSTM result, the the neural network result, is given in orange. Okay, so you can see again that it mostly behaves. Okay, the neural network output behaves similarly as your true data. Okay, and to check how good or bad your model is, okay, we have the statistics. Okay, so the usual statistics that are given. You have the R squared, RMCE, and mean squared error, which is 98. Okay. Oops. Right. Okay. So I think that's the end of my part on dynamical systems. Are there any questions? I actually can't see the chat.
Hi, Vivien. Questions haven't come through yet. So we can wait a few minutes. Guys, I suggest we have another short break. And in that break, you can put down your question and Dr. Visaya can answer it for you. But then I'll carry on at, let's say, 10:55.
11.
Or 11. Let's make it 11. I'll carry on at 11 with the looking at an actual problem and working through it, just so that you can see how the data cleaning is done.
Sorry, I mean, my slides, I don't know why they're not working. Okay. Okay, we'll start in 1 minute.
Okay, good morning, everyone. Again, welcome back. It's 11 o'clock. There were no questions for Dr. Visaya, so I'll continue. Please, if you have any questions, put them in the chat. In the chat, I put a Google Drive with links to papers and the data. Please let me know if you're having any issues accessing that. I've also put the links to what Vivien and I referring to as 3 tutorial problems. The first one is build your own detection model using OpenCV and Python. The next one is number plate recognition using Python. And then the third one is how to use Google Maps API in Excel. I'm going to go through that one with you, just touch on it briefly. So if you want to do any of those things, please, by all means, go for it. I would suggest you do the first 2 at least, just so that you can essentially build some, I guess, intellectual muscle memory with the work we covered today. So the first data set I'll be looking at is from the US city of Georgia. The reason I chose this data set is because it's the one used in the most publications on traffic modeling. It's been used a lot recently in traffic modeling using machine learning and AI. So it's actually a nice set to use. Just to give you a sense of Georgia's 300 miles long, 230 miles wide. When you look at how these models are put together or how the data is presented to you, just to give you a sense of understanding what is what. The inventory side, that's the side that you're measuring, right? But you can see that the direction then becomes important. So it's from south to north or west to east, right? So if you're on that side of the road or you're on that side of the road, okay? So if you recall earlier, I spoke about, I'll have a look. I spoke earlier on about how if you're an observer who is moving with the traffic, right, you get this problem happening of vehicles moving towards you and vehicles away from you, right? So essentially cars going backwards are actually just going slower than the observer speed. Okay, so these are the things that then become important, because essentially if you're putting an observer, say, on the median, right, then cars are coming toward and moving away. Okay. Georgia is divided into all these counties and districts and sub-districts, and you can see what's nice about this data set is that the roads are classified. Now I'm going to show you the data set now, but you'll see these are the main roads, and they're all well documented, etc. And they all just combine in the city center or the state capital, I guess that would be, and move out from there. Right? Now, in terms of sensors on the road to measure traffic, right? The reason you have different colors and squares and different shapes, etc., is because it's the kind of road that they have. So they have sensors on roads in rural communities, roads on the motorway, roads that are in through suburbs, etc. So that's what that means. But this just shows you the distribution of these sensors. The reason why this is such a popular data set to use is these sensors have been there for a few years now, So there's actually a few years worth of data that can be accessed there. Now, if you get involved in this area of research, or you're just interested and you want to look at problem here, you'll notice that all the data is presented in terms of AADT. That's the annual average daily traffic. So the way this is measured is on individual road segments. The data is collected by a traffic counter. You can have an observer as well to record traffic. Or, as I said earlier, you go to the GPS data provider, so the trackers, etc., in your car, and you actually ask the GPS providers for that information. This is a newer camera that essentially monitors the road. The two codes I gave you are actually about this, where if you have a camera, can it see the number plate? So you do a visualization, can then a counting exercise. So that's the two exercises that I gave you for a tutorial, right? That's where the data comes from. Now, because AADT is an average, right? One of the issues in data science that I don't think they covered in depth yesterday is the fact that language is probably your biggest obstacle. If you go into an area that's not your main area of research, so if you know nothing about traffic modeling, for example, and you go into this area and you come across this AADT, so average annual daily traffic, right? The first thing you'll notice is average, fine, that's the mean that you understand, but they have annual and daily together, and you're like, what the hell are they doing? These are two different times, right? But essentially, it's the total traffic for the entire year divided by 365. So it's annual, it's over a year, and then they get a daily amount. Yeah? There are problems with calculating this, for example, using AADT, for example. If your equipment's not operating for 365 days, you're going to get a miscount. Seasonality is not taken into account. Day of the week biases are not taken into account. So I'll give you an example. Schools are closed at the moment. So if you've been driving anywhere, you'll notice there's less traffic, but only less traffic in certain areas, right? The main roads are still as busy as they've always been, but it's the roads around schools that have become very quiet, right? There is no way you could have predicted in January that COVID would cause a shutdown in July so that it would affect traffic, right? And that information needs to be taken account of somewhere, right? So not only do you need the traffic data, but now you also need data related to public holidays, weather conditions, was the road being maintained? You'll recall the M2, I think it is, was under construction for about 6 months. The M1, I think, was under construction for more than a year, right? And all of those things affect the traffic, right? So if you have this traffic over a few years, you have to be aware that there may be things that you are seeing in the data, but you have no idea why they're happening. Okay? And then, of course, the important thing here, what you want is a growth factor. So how many more cars are there on certain segments of road? So do you have to do something that actually is going to change the way that road operates? Okay, that's essentially what this information is for. So on the data set, you'll see it comes like this. These are the station IDs, and that's where all the stations are. You get a class, and you'll see in terms of the class, these are the kinds of roads that you have: rural, minor, rural, principal, urban, right? So these are all the various classifications. Latitude and longitude, that's the position of each sensor. That's the annual average annual daily traffic, right? So 2019, on average, 4,080 cars per day went past that sensor. 12,300 went past that one. 14,700. So you can see, and the big numbers, right, are obviously important roads within that community. Now, the first difficulty you'll have with this is an incorrect assumption, right? And the assumption, I would make, and probably anyone else would make, is that the rural roads are not as busy, right? But you start seeing weird numbers like this, 11,100 on an urban minor road, right? On the principal urban road, you can see, okay, the numbers are fairly huge, but suddenly you have a minor road with the same numbers. Same here, right? You have these urban, so these are roads moving through communities that actually have these big numbers. So to avoid that danger of making assumptions with very little information, right? I'm going to show you one or two ways of doing it, but try and avoid making any assumptions. Let the data rather tell you, because if the data can tell you what's going on, you'll then have a better sense of what your data is saying, and you can give better results, especially if you're a consultant. Now, okay, I'll give you a wrong way of doing things, right? So the first wrong way is, I did geography up until standard 8, it was a long time ago. So when I see latitude and longitude, the first thing I think of is, okay, does that mean we have to measure distances like this? Okay. Now, there's nothing wrong with measuring latitude and longitude distances using this approach, where you assume the Earth is not flat, but a sphere, and the path is following essentially a spherical path. And I said it's not a straight path, but a spherical path. Yeah, nothing wrong with that. And it allows you to measure essentially birds, what do they call it? The bird's eye view, the way a bird would travel from one point to another. But what it doesn't measure is roads, right? It doesn't measure the distance on the roads that already are there. Okay, so this is the formula you can use in Excel. You can get, and it gives you nautical miles. So this is easier to do on an ocean. That's why you get nautical miles, because there's no roads, only straight lines, right? I mean, that's kind of the obvious one. And you can convert that to kilometers. So from nautical miles, you convert to meters, and then meters to kilometers, right? Now, this is probably the worst way to do this, because number one, you're modeling traffic. Number two, traffic uses roads, various kinds of roads. But there's a third problem that has crept in because of technology. And that problem is the fact that we have maps on our phones. So when there is congestion, say on a highway, your Google Drive will actually tell you, look, you can stay on this road, but you know there's a traffic problem. You'll be stuck in traffic for 20 minutes, or I'm going to recommend this alternate route for you. If you take the alternate route, you'll get there quicker. Having these maps has actually changed the entire dynamic of the way cars move through a city environment, and even a rural environment, but very specific to a city, because sometimes the route that you are advised to take to avoid traffic goes through a very quiet suburb where kids are playing in the street, you know, pets are walking around, etc. And you find cars traveling 80 to 100 kilometers per hour on a very narrow road through a suburb. Right now, that's obviously dangerous. But the person who's driving was basically told by an AI, hang on a second, please take that road. It's better for you, you'll get there quicker. So this is where psychology becomes important, because on average, the speed at which you will drive on that road is probably the same as you would drive on the main road. So no account is taken of the fact that you actually have to reduce speed. So even if the map has taken that into account, you as a human being, your thinking is, okay, if I've traveled on the highway at 120 kilometers per hour to get from point A to point B, I must now drive at 120 kilometers per hour through this suburb to also reach my destination. And that's not true, right? These Google Maps and stuff are very, very smart. Right? They take everything into account. Now, so then what do we do? Well, what Google allows us to do is essentially become a Google developer. If you become a Google developer, you then have access to all the data that Google makes available. right? For free, actually. Well, for free up to a point, I will say, right? So, okay, before I show you, so Google makes several things available to you. The first one relates to traffic, maps, etc. And the 1 tutorial I gave you is on pulling that data into Excel. And then the other one is where you can actually get what's called the matrix, and it's matrix traffic something, and that can tell you about road conditions, etc., over a long period of time. Okay. Now I want to share with you. I'm going to share with you something else now. Just give me 1 second here. Okay. So, right. Okay, so now this is, once you start a Google profile, that's what your profile will look like. Okay. This stuff you can learn to build anything with Google. It tells you what they have available, etc. Right. So if you go to the products page, okay, so this is, okay, those of you who want to earn money from Google doing things, there you go. If you want to grow your user base, if you want to develop high quality apps, you can use Android and cloud. TensorFlow is an open source software library for machine learning and deep learning, in fact. If you want to develop applications for the web, and this is the Firebase to build better mobile apps, and Maps platform, which is the one that's important to us. Maps platform is the one that allows you to see distances traveled. Okay. There's a WebGL, so this is a graphic interface that can allow you to use the power of the maps or Google Maps. Here, with this one here, you can see, because Google is actually monitoring traffic 24 hours a day, you can actually get some local intelligence on areas. There's a code lab that can show you how to include some of this information into a big data analysis project. And then, of course, clustering with JavaScript. Okay. So what is, there's the distance. Okay. So what's interesting here is, and this is a problem you will have if you're going to tackle this as a research area, or even just trying to do this for fun. Because you now have different routes that a piece of mapping software will give you, you end up having to ask yourself, what is the most probable route someone would take? Okay, so in the past, when roads were built, there was only one main road through a town, for example. Right now, because of things like Google Maps, you can avoid a town altogether, or you go down a side street instead of the main road to avoid traffic. And you have all these knock-on social, psychological effects that were not there before. And so routes is one of them. Places is another one. If you know, for example, that traffic on a Friday is motivated by, so the reason there's an increase in traffic on a Friday is because people are going to the bank, for example. Now, obviously, that's not the case anymore. And I don't think any of you were born when the bank was a place you had to go to probably once a week or once a month to draw money, deposit money, etc. Now you do it all electronically. So all these pieces of information then become important, because if you know, okay, traffic in this area is because there's a big shopping center, right? This helps you understand why traffic is moving the way it is. This helps you understand the various routings that traffic will take. And then this just gives you the overall picture. So that's almost a global view, if you like. And then these are the two local views. Okay. Roads, identify roads by coordinates. Distance, times and distances for multiple origins and destinations. And then directions, multiple transportation modes, right? So this one is the different modes of transport: car, plane, bus, etc. This is this distance matrix, which is the one I mentioned, tells you how far point A is from point B in terms of the roads. And then it's just identifying nearby roads. So here you get it in JSON or API. I'm going to use Excel. So Excel uses a JSON file. And if you read through this, well, there's the JSON file. you get an example on how to actually use this in your Excel to measure distances. Right, you can see there latitude, longitude, or you can put the name of the place as the origin. But it actually works quite nicely with latitude and longitude to give you the information that you need. Okay, you can put in options here of avoid highways, avoid tolls, unit system driving options, and transit options. Transit would be trains or planes, etc. What is your travel mode? So if you look at Google Maps on your screen, it has different travel modes. You can be walking, bicycle, motorcycle, or vehicle. I haven't seen trucks at all, but I'm guessing that would just fall under vehicles. Okay, so that's what you can do with that. Now, if we go to there, right? So this gives you an overview again of what you can do. So those of you who are interested in doing things that are graphic driven, right, you'd have to look at that, because especially if you want to do anything with building a map on your phone, maybe directing people to restaurants or the top 10 restaurants or something. So you would need a overlay like that for your data. So underneath you'd have some data analysis happening, but to represent that data, you do a visual representation. So if you recall yesterday, that's what they spoke about in great detail. Right. Now, a warning from, so I'm an applied mathematician. Well, first of all, South African, then applied mathematician. As a South African, we just click yes for everything, right? I don't know anyone who's ever read one of those warnings or help things or anything to say, use this or use that. That's very dangerous when it comes to things like this, especially where someone says they're going to give you a certain amount of stuff for free, but you must obey the rules, because it's very easy to then break the rules without realizing you're breaking the rules. Yeah? One more thing that's of interest, just to alert you to, those of you who are into gaming, there's Google Stadia, right? Stadia. What that allows you to do is play very complex games anywhere on any machine, just logging into your Google account, because the game itself sits in the cloud. You don't have to download the game, but you can play the game. I don't know if Stadia, I don't know in South Africa if it's such a big deal yet, but I know in the US, you can do this quite comfortably. So if you want to play, what's that, 27 Cyberpunk, for example, on your phone. Okay, at the moment you can't do it through Stadia because it's quite big, but eventually you'll be able to do it through Stadia, where you can play it on your phone, through a web browser, a Mac, anything. Right? Asset tracking is also something important in terms of innovation. If you want to design a piece of code that's going to track cars, going to track laptops, going to track personnel, that's also something you can use this for. Rides and deliveries, so that's essentially saying if you want to build your own Uber, right, you can do that. Retail, most businesses in a particular area are actually on Google, so you can combine things, gaming, retail, and deliveries. So if people are playing games, the example they used yesterday was the pizza, where if you in Facebook, you can also order pizza. The way you would do that yourself is combining things. Like if you knew someone was doing gaming, during gaming they might get hungry, you could put a button in the game to say, right, the food or the restaurant or the retail that's close to you that delivers food is ABC. Click on one of these links and you can get your food delivered. You can organize the delivery through that. But you as the developer or the builder of this data application, you would do all of that, right? So, okay, here's how various businesses are using this, your inbox, etc. Okay? So that's fine and well. I think that works quite nicely. Pricing, $200 free monthly usage. That's quite, for us in South Africa, it's 200 times, I think 12 or 13 at the moment. So that's quite a bit of rands you get for free that you can use. You pay only for what you use and they're here to help. So obviously, if you're building a big platform, you're gonna exceed that free usage probably in the first day. Right? If you're building a platform where your users are going to have to access this information on an almost daily basis, right? Okay, documentation I skipped. So yes, more customer stories, right? And what's interesting, and again, this is just speaking to innovation or anything innovative you want to do in data science, you can actually go to these companies, see what they've done, and then ask yourself, okay, what would work in South Africa? What would be a good thing to work on, a good thing to invest in when you're using all this data, right? So that's the one thing I wanted to show you, is to say that, look, in this particular talk today, we're looking at traffic, but traffic is so much more because of data science. Traffic now includes problems around business, problems around driving style, problems around positioning of schools, because people can get to schools a lot easier because of the availability of this data. Right. So now I'm going to get back to my talk. Okay. And yeah, it's actually easy to register as a developer. You get an email to say, congratulations, you're a developer, go forth. So now I want to show you this, right? So I was banned when I actually did work on this. And the reason I was banned is the way, because I was using the API, the Google Maps API, to find lots of routes over a very short space of time. It looked like I was using this for business. And if you're going to do this for business, you actually have to notify them, right? And I'll actually show you in the Excel spreadsheet where this created a problem, right? So yeah, just be careful. That can happen to you. So now I'm going to open the Excel, and we're going to just do some stuff in Excel, and then we'll stop for questions, right? Okay. So you have access to this data. This is the UK one. It's ADT, the average annual daily traffic, and the percentage of trucks. As I've said to you before, you have a station ID, function class, latitude, longitude, AADT for each of the years. Right. Now, why I'm using Excel and not R or Mathematica, anything like that, is when you just get raw data like this, right? All those packages are actually not going to work, right? If you try and put this into Mathematica, the raw like this, yeah, you're not going to get very far, right? So if you look at cleaning up some of this data, right? So you can separate out this list into latitudes and longitudes. As I've told you, I calculated nautical miles and I calculated kilometers. Now, this is obviously incorrect, right? Because there's no way vehicles would travel 0.0018 kilometers. Okay, that's just not going to happen. This is what happens when you make an incorrect assumption, right? Because here I assumed it was latitude and longitude. Using latitude and longitude, what is the direct distance between these two? Right, it's that many miles, and it's that many nautical miles, and then that many kilometers. Okay, so yeah, obviously a very, very bad decision. Next bad decision, right, is this one here. Okay, where you can take the traffic density, and if it's average annual, you divide by 24 to get it to hourly. You can divide by so if you take that AADT data and you just do a blind divide, if you like. So if that's average annual daily, to get hourly, you will divide by 24. That's definitely not correct, but mathematically it's fine because it's an average, so you can do that. However, if you just divide by this, you're getting incorrect information because that's not true. Right? There's seasonality involved in travel. There's, depending on the time that you are traveling, there's also things that can happen. Right? Now, I want to just do this one more. Okay, and then okay, so I just did a log. I wanted to see something. That's the percentage of trucks, right? Now, obviously, I was banned, so I can't actually show you where I worked out all these distances in kilometers, but I can assure you the kilometers are a lot further than this, right? Because I had to actually delete that API before I could actually get here today. But I suggest you actually try it, right? Try it and see what happens. Now, the next advantage that you get from doing things firstly in Excel is Excel can give you suggestions. So if you want to divide your roads up into categories, right, it can actually give you how many vehicles in terms of AADT used rural major collector roads annually in total. Right? That's the total. So if you take all the information you have, the total for 2010 is that, right? And you can calculate all the other totals like this. Now, how does that happen? Okay, so those of you who are UJ students, you have access to the whole Office suite. You just download it from Ulink. And I think most universities actually give you access to the Microsoft suite of products, right? The first thing you would do is, if you go to, hold on, you would go to options, right? Now, if you go to the add-ins for your options, you'll notice that these are inactive, but you are allowed to activate them, right? So you have an analysis toolpack, right? Analysis toolpack in Visual Basic. If you're working with dates, right? Sometimes if you're given a date on a weekend and you want to ask whether or not that particular date is a weekend or a weekday, that's where you need that. European currency tools, I mean, that's obvious. When the euro was introduced, it created all manner of problems. Data streamer. So this is if you are building an application that's taking data continuously. So if you look at IoT, so the Internet of Things, there's a lot of applications you can build that stream data continuously. If you think of how Google Maps works, it basically streams millions of data points every second, right? From everyone whose cell phone is on and you're driving a car, you're walking, etc. This is a nice one to use because you can do basic optimization problems using Excel. Now, this is a neat one to try because it basically means that if you want to maximize or minimize subject to constraints where you have data, you can actually do that using that add-on, right? Or add-in. Okay, so just remember that. I'll show you again how to get there. File, options, right? And when you get to options, you go to add-ins and you just click on it and it's an Excel add-in. Here you can pick what kind of add-in and you can say go and it'll add it for you. So if you look at my Excel screen, you'll see I've got the data analysis toolboxes open, right? So if you click on that, right, it highlights my data, right? And then it's going to say to me, listen, we've gone through your data. We can suggest that you look at these 2 or 3 things, right, that we've picked up. Now, again, I'm just going to state this to be clear. This is if you've been given the data set cold, right? By cold, I mean you are not involved in generating the data. You're not involved in analyzing the data as yet. The only thing you get is a database or a set of data points, and you're told go do data science on it and tell me something important, right? So yeah, you'll see that you get almost a discussion point about your data almost immediately, right? Frequency that tells you they analyze latitudes. So it tells you points in terms of latitude that are close together. Classes of roads, obviously that class, those two 5R and 4R have higher truck values. Now this should send off red flags because technically trucks shouldn't be using those roads, right? Trucks that use these roads are going to cause a major problem for people who live in those areas, right? So trucks that carry goods should actually be using the highway or the motorway. So this is immediately an interesting observation. The left 121 has notably higher numbers in 2019. Well, yeah, okay, that's neither here nor there. But then what's interesting is it can say these are areas of your data where we notice discrepancies, right? We notice that you can sort your data using these characteristics, a functional class, for example, and number of vehicles. And if you do that, so you get, okay, where's my mouse? You get there. So I've labeled this as suggestion, and this comes from Excel. Excel suggested this to me to say, let's look at the sum of trucks who use the roads for each one of these roads. Right? And you can see immediately rural major, rural minor has the most trucks. Right? And that's the conclusion it reached, which is why I wanted to actually do this one, because you can see that information now right in front of you to say, okay, I can see that those two routes use the most vehicles use those two routes. Right. Now, from here, you would then take this into R, into MATLAB, into a Mathematica, whatever you want, and start doing other things with it. Now, if you looked at this again, now if you had weather data, okay, and you knew the date on which some of these measurements took place, you could probably do something combining weather with data. Right. Now, I'm going to look at a different set. This is the UK's data, right? And if you look at the UK, you'll see data has a count, it has hour, 7, 8, 9. So anything before, so it's almost like they have a curfew, right? They only start counting traffic, you can think, at 7 o'clock up until 6 o'clock. Okay, and most of the data is like that. Right? Those are the hours. You can see these are dates on which the data was taken, measured. You can see this is a raw database, so that the dates, the year, position, direction is all over the place. Right? What's interesting here, you get, is it London, where in London, etc., etc. Again, you get latitude and longitude. You get different kinds of vehicles, right? A pedal, a bicycle, 2 wheels, it's a motorbike, cars, buses, etc. Right? So you see the data from the European, in most European countries will be this detailed, right? It'll define the different kinds of vehicles. These are heavy vehicles with different kinds of tire loads, etc. On a particular date, at a particular time, that's gone past a particular sensor. Right? So you can see this, when you get data like this, you can actually do a whole lot more with it. Now, if you look here, you actually have 369,588 data points. That's big, but it actually isn't that big, because when you do big data, you get data sets that are bigger than this, right? Now, I haven't done anything with this. I don't know what peculiarities it has. So there you go. See, too much of a good thing. Boom, crashed, right? So yes, these buttons are convenient, but when you have such a big data set, and I can tell you now, this is probably small compared to some things you can get. So financial data, for example, this is probably the amount of data you'd get for one day, right? So many data points, depending on what you're measuring. So there you go, right? You can immediately already, this thing has said, no, can't do it. Don't understand what you want me to do. Okay, I didn't load the others on, right? So Excel is powerful, it's useful, especially if you want to get just a first glance or first idea of what's happening with your data. But you then also have to worry about, okay, it is Excel, right? It's not built, it's not purpose built for data science. It's had stuff added on so it can do data science, right? So for the tutorial this afternoon, what you can do is do searches along the various classes of road. Right, see what you come up with, because you've got both the UK data and you've got the US data there. Dr. Visaya, I think, has got data from the Philippines. And that, you can imagine, has also got very big numbers, right? It's got peculiarities there in terms of what you can do. Okay, so was there a question? No? Okay, so you can see this has got 27,000, the other one was 36,000. So it's almost 10,000 additional points that are sitting in the UK data set. So here you've got 30-something thousand across years. Right? So you've got 2019, 18, 17, right, all the way down. I think that stops at 2010. So this is a significant database in terms of having information for you. So if I were to ask you, right, if you were trying to open your own business, trying to be innovative, how would you use this, right? So I don't expect you to tell me now, because if you're going to come up with something that's going to make you a lot of money, well, I don't want to know about it, right? That's your business. But these are the kinds of questions you can ask yourself using freely available data, right? This is free. I just went onto the internet, search for search for GA400 traffic data. I got it. Your next step as a data scientist would be, okay, Prof. Momoniat discussed modeling. Dr. Visaya looked at modeling with discrete systems, looking at chaos, etc. How could I use those things with the actual data to come up with a product, something to sell, something that can help a business, etc. And that's what the SAS people were referring to in terms of just keeping an open mind. It's using your imagination to say, I've got all of this, right? What's the important features of this? And I've shown you that to get important features, you can use built-in tools if your data set is small enough, or you can do the other stuff as well. So if you go, so sorry, someone's asking me about if I get analyzed data, right? Analyzed data I put in from here. I can show you. You actually have to add it in from here. Sorry, add in. Where is it? Where is it? Where is it? Hold on, sorry. I'm just looking for the one that shows you what's on the ribbons. Oh, there's a customized ribbon. So if you go to the ribbons, you can add it here. What is it? Analyze data. So it'll be here. But so just check your Excel. It should be here somewhere, right? And then you can just add it to the ribbon. Sorry.
Does it depend on the version of the Excel? I mean, it appears in mine.
Yeah, it depends on your version of Excel. That's right. Yeah. So I'm using obviously the staff version, right? Which has everything. So there, see, I added in the data. So this was off initially. Then I clicked it on, and if you see what it gets, it transformation data, query, sort, filter, data, tools, forecast, and outline. So just check the one that you have. You may have to just tick that box to add it in. You have to tick the box for add-ins, so that when you go to add-ins, the add-ins will actually show. Otherwise, you'll have the add-ins, but they won't show. Sorry. So it's customized ribbon, and then you just go look through the main tabs here. There's also developer, right? So the developer becomes important because I've made myself a Google developer. So to use the Google developer tools in Excel, you have to activate the developer there, and then obviously the add-ins. You can see if I just ticked add-ins, which means that I can now add the add-ins. Powerpivot is also something that's new. It's not a standard one. Powerpivot gives you those pivot tables, but it's used when your data set is very big. Okay, that's how you'd use Powerpivot there. Okay, so that's it for Dr. Visaya and myself. If you have any questions or queries, you can ask us now. I'll be happy to answer them for you. And I've put in the chat links to the exercises that I spoke about. The first one is, so obviously I said build your own vehicle detection model, right? So the minute it says model, that's the stuff we were talking about. So how are you going to build a vehicle detection? So How do they know it's not a bicycle that's going past, but a vehicle? Automatic license plate or number plate recognition. That's also a nice one to try, and just play with it. So why does South Africa have Poppy? If you look at this one here, so you as a student can do this. If you get photographs off the internet of license plates, it basically means that with this, you can look at a photo with lots of cars on, and your software will use image processing to then give you the number plates. Now, that is almost touching the line of invasion of privacy, because you then be able to say, this car on this date at this time was at this point on the highway, right? Or wherever it is you're measuring things. Same with this one here. Although I think this one is fine, but it's not as specific. So you're just saying, is it a vehicle or isn't it a vehicle, right? This one here using Google Maps API. Well, obviously you can say I got into trouble, right? Because I use this, but I then, because of how my machine is so fast, rather than querying one at a time, I've got a multi-core machine, so I queried 11 streams at a time, right? So the way Google looked at it was, it's 11 people accessing the same amount of data, and they don't allow that. I can access it. It's one person can access the data as many times, up to the free $200. But if you have a multi-core machine, you need to be careful, because it will look like 11 people, right? So you need to be aware of that, that your computer is very, very powerful, especially if you've got multi-core machines. If they can look as if they're a server when you're accessing certain services on the internet. Okay, any questions? No, I didn't see any new questions coming through. Vivien, do you have anything you would like to add?
None really, but I just want to ask, why were you banned again?
Oh, I broke. So I'll if I show you the thing, you'll see what I violated. Let me show you.
So just in case some of
yeah,
our
please don't do that. Yeah, right. You guys, please don't do that, because yeah, I woke up to this email on a Sunday morning. Right? It's not the way you want to start your Sunday. Okay, so
but it's quite useful.
Yeah.
The Excel. I mean, I haven't.
Yeah, and this is accidental, right? So I didn't set to do this on purpose, right? Please understand, right? So we're happy to see developers use the platform. However, we detected that, and I called my API travel distance. It could be scraping data. Now, scraping data, the definition, they have a definition for scraping data, which is essentially pinging the database in a way that looks like you're harvesting all the data. You're not really using one piece of data for one thing, right?
Okay.
And it took me a while to figure out that it was because of the fact that when you activate all the data stuff in Excel, it actually uses all your cores. So it looks like it's 11 computers rather than just one. Okay. So it's that one. Your previous access to maps. So they banned me for 24 hours. So obviously that was because of the traffic generated by all the queries. And so, yeah, I had to go and have a look at that and just see what policy I broke. So again, as data scientist, you can see this anyone can. So you learn from it. You then say, okay, I need to do something different if I want to do that. Okay. So yeah, just be careful. The free stuff is really brilliant, but just follow the rules, right? And you'll be fine. You won't have any problem.
Yes.
Okay. Any other questions?
Any other questions?
Well, I guess there's something in the chat. I've noticed that if you set your ping time to around 3 seconds, yeah, that's correct. Mine was like, I think it's 11. So mine would have been 11 queries every point something seconds, right? Which is scraping. I mean, they're justified to say it's scraping because there are millions of people accessing it. So yeah, I mean, this is not, yeah, I should have just done exactly what you said there. Look at the time, and 3 seconds, I think, is kind of enough. You recall Vivien spoke about why do people use 15 minutes on average in most of the papers? This is why, right? Because even when you get traffic data, the free data you can access is usually the one that's not very detailed, and it's usually either in 5-minute ticks or 15-minute ticks. So that's where you get the 5 and 15-minute thing coming up. If you request tick data from any database, you will have to pay. So tick data is real-world data being generated in real time. Okay, and tick data is very expensive. You can get tick data for financial data, for example, or tick data for Bitcoin, right? It is massive data sets. Yeah, depending on what you want to do, obviously it's up to you. You need to decide if it's worth it or not, because you may actually be able to do the innovative stuff using the free set of data rather than paying for the data. But that's up to you. It all depends on the application, etc. But my gut sense would be that over the next few years, as computers, again, the next stage in computing, where if you've seen the adverts on YouTube, you'd see that Intel now has a graphics card, and all Intel's machines now come with the Intel graphics card. And I've got the NVIDIA graphics card on my machine, simply because NVIDIA works with Mathematica if you want to do data science. The Intel one, yeah, I haven't seen any games or anything using that, but that's something to keep an eye on, because that seems to be big innovation. For those of you who are into gaming, you know the AMD chips also way better than the NVIDIA chips in certain machines. So yeah, there's a lot of competition in this data space around hardware. That's also interesting if you want to build applications, because your phone, a multi-core phone, some have got 8, 12, or even 16 processors in the phone, whereas your machine computer doesn't have that many. And so your phone sometimes would be more powerful than your computer, depending on what you're wanting to do. Right? You can actually use your phone to do some very nice things. Yeah, but we don't have time to show you that. Okay. So thank you, everyone. Vivien, do you want to say anything?
No, we just want to thank everyone for attending today. And then if you have any more questions, you can also email us. But we also want to remind you about tomorrow's workshop. It's going to be more interesting from, well, yeah, it's going to get more interesting from, well, it's also interesting today, but it's going to be more interesting from.
So I think what Vivien is saying is that from tomorrow, it's heavily into the computing aspect of things. So those of you who are attending the workshop to actually learn computing skills from tomorrow is where that will happen. So I think they're doing Q thing is tomorrow. Let me just go to the top of my slides. If I'm not mistaken, I think Q learning is tomorrow. Oops. Yeah, yes. So Q learning is tomorrow, right? And then, so Q learning, missing data, those are probably the two biggest issues. It's learning and missing data that you'll come across. And then Azure. So Azure is the Microsoft comparison to what the Google developer thing I was using, right? I think Dr. Visaya and myself are on a group looking at, I think, is it Azure for UJ, right, Vivien? I think the email came, yeah. So UJ is thinking of getting an Azure license for students to use. But we have to evaluate it still to see what you can and can't do. But obviously, if we have a license, then that 3-second thing falls away. We'll actually be able to use big data and cloud computing, which is actually where you want to be if you're actually building a real application. Okay, so thanks, guys. Thank you very much. And please don't forget tomorrow, 9 o'clock. And yeah, if you have any questions, as will be mail us. But yeah, thank you for your time. And we hope you benefited from this.
Okay, thank you, everyone. Thanks, Prof. Momoniat.
Have a good afternoon. Keep safe, guys.
Bye-bye.